Welcome back to Battleship Systems. Today we're in forward main battery plot on the Battleship New Jersey, and we're here to talk about the Mark 8 Rangekeeper. The Mark 8 Rangekeeper allowed battleships to layer their guns in such a way that they would hit the target with their projectiles. This Rangekeeper was made by Ford Instrument Company, and it started its life out as a Mark 8 Mod 11. But it's had a number of modifications or alts done to it to make it more effective.
Before we get started, I've been told that I should be wearing a hat when making these videos, so maybe that'll be my New Year's resolution. See how it goes. The Mark 8 Rangekeeper is the most advanced mechanical computer ever made for the Navy's largest guns. Aside from connecting the directors to the turrets, it performs 4 functions. That's tracking, predicting, ballistic computation, and stabilization. The tracking part determines where and how fast the target is moving around the ship. The predicting part determines the forces that will move the projectile when it's in the air and solves for how to compensate for them. The ballistic computation is like the software for the Rangekeeper. It comes preloaded with everything that's in the range table for every projectile that the ship can fire. It tells us how long it'll take for the projectile to reach the target. And the stabilization part makes sure that the pitching and rolling of the ship doesn't mess up any of the computations. Tracking starts with the director determining a line of sight. But how does the Rangekeeper get that information from the director?
Over here is our observed director train dials. So this is where our director's position is relayed to the Rangekeeper. The indications for director train are on the center dials. The automatic are on the outside. Now normally this would operate a servo to keep those in line. But if that servo breaks, you could manually crank in the observed director train from this dial here. Now what would a Rangekeeper be without the range? And this right here is where you crank in the range.
You can crank in the range manually up to 72,000 yards from the present range knob.
It has a modification done to it to where if you flip the switch to auto, instead of entering the range here, you could enter it over here from the Mark 13 radar. As the radar is tracking, it is constantly updating the range.
Okay, so our director has found the target and is sending us observed director train and the range into the Rangekeeper. But we'll notice that observed director train is moving constantly to the left or to the right. And that's because the director has to move to the left or the right in order to stay onto the target. Now that could mean one of 3 things. 1, that our ship is moving. And number 2, that the target is moving and the director has to move to stay on target. Or number 3, that both are moving. Obviously, both the target and the ship are moving, and it's the tracking section of the Rangekeeper to break down that movement of the director and determine the target course and speed. The tracking section resides in the upper part of the Rangekeeper. It's mostly automatic, but requires a few more hand inputs from the operator.
So for order for a Rangekeeper to hit the target, it has to know where the target is. So it all starts from this observe line here. This is where our director is pointing to the target. Now this represents our line of sight to the target.
We fix this by cranking our generated target bearing until the observe pointer matches the target bearing. The observe pointer sits on the own ship dial. Where the pointer meets the index of this dial represents your observed relative target bearing, or basically where the director is pointed on your ship. The smaller dial next to it is just a fine version of what's displayed on the big dial. So if we want to see what the actual observed relative target bearing is on this range keeper, we look at the dial, it says about 70, and on the fine dial we see it's 79 degrees in about 10 minutes.
Now this dial on the outside is our true target bearing. So it's based off of this crank here, but it's also can be ran from the ship's gyro.
So again, if you want the true target bearing, you take where the ship is pointing to the outer ring dial, and that gives you about 299 degrees and 20 minutes. And the dial above that is our target dial. It shows us where the target is moving. If we read the center target dial against the fixed index target bearing, it'll give us our target angle, or the angle of the ship relative to our own ship. The middle ring, again, comes from the ship's gyro and represents the target course.
And the dial on the outside is the true wind.
The cool thing about having your target angle dial and the true wind dial sitting on a compass dial is that as your ship is maneuvering and your course changes, these dials update automatically.
Now, if you remember back to Fundamentals of Fire Control Part 1, we have the line vector diagram of the external ballistics, everything that affects the projectile during its time of flight. Just for a refresher, this vector here represents our ship speed. So obviously the projectile sits on a ship. As it fires, it's moving because the ship was moving. This vector here is the wind vector. It affects the projectile. And then this is our target vector. Since the ship target is moving, we need to make sure we account for that as well. So that sets up the angle part of the exterior ballistics line of sight diagram. But vectors have an angle and a velocity. This is where we set the velocity of those vectors. So the wind speed up here is measured in knots. The target speed here is in knots. Again, this is an estimated value, at least initially, and the ship speed is entered here. Ship speed can come from the ship's pedometer automatically. These two dials here are the rate dials. This one says range in knots, and it shows whether it's increasing or decreasing. And then we have deflection, which is moving to the left or the right of the line of sight. So basically you're breaking our vector down to how much the target is moving in and across the line of sight. These two devices over here are the speed and course change indicators. Now the way you use the speed and course change indicators is you ignore them unless you find that you're constantly drifting to the left or to the right of the line of sight, or if your present range calculation keeps getting wrong and you have to keep increasing and decreasing it. Probably means that your initial estimate of the target speed is wrong or target angle is wrong. After all, the ship's probably going to be doing all kinds of maneuvers. After all, they're being shot at. So what you would do in that case is, if we notice our director is constantly pointing to the left, we need to add bearing to it. So we look at these speed course change indicators and section for plus B. So on the speed indicator at the plus B section, we see an arrow pointing up. That means to add bearing, we need to turn the ship's speed and crank it this direction. Now, same thing for the course. Right now, if we want to add bearing to the course, we see an arrow pointing down, and we would need to crank the course dial this way.
When you read the own ship dial against the target bearing index mark, that's actually generated target bearing. The range keeper will automatically move this dial back and forth based on the deflection rate. If you find that, even though this dial is moving back and forth, that your observed target bearing is still online, then you've got it right. But if you find that it's moving to the left and to the right, we need to either correct that or change the rates. And this process of generating and correcting values, whether that be range or deflection, is known as rate controlling.
You probably do this all the time when driving. If you want to switch lanes but there is a car in your way, you step on the accelerator to overtake the car. Even though you're paying attention to the road, in your mind you generate where you think the cars are in the lane next to you. Then you periodically look at the lane to observe if your estimated location is right. If not, you will have to either increase or decrease your rate. That's rate control. Battleship sailors watch these predicted train values over time as the rangekeeper automatically moves the dials. Okay, so if you haven't noticed by now, the tracking section of the rangekeeper doesn't care where your director is pointed. All it's concerned about is target motion, which is computed down to those two rates, which is range rate and deflection rate. From those two values, the tracking section makes something called generated director train. The generated director train is basically where the tracking section thinks that your director should be pointed based on the rates it already has, multiplied by time. Speaking of time, over here is a clock. So another transmitter is the generated director train. That is based off of this one here, and it says where the rangekeeper thinks the director should be pointing. This generated director train is sent up to the person training the director. The director train indicator contains an inner dial and an outer dial for both fine and coarse bearing. Those inner dials show you the generated director train so you can see if you're matching. The Mark 8 rangekeeper is a battleship system, so it needs to continue tracking even if parts of the ship are damaged. One example of this is if the directors were hit and destroyed, you can set up the rangekeeper to use its generated director train as the director train input. It's like telling the rangekeeper it's always right. Another example is the resiliency of the timing system. Constant torque is required to drive the integrators. If the timing motor ever breaks down, there's a manual power crank where you can drive the tracking section of the rangekeeper by hand. There's also a cool one up at the top here. There's deflection rate. So deflection rate is actually transmitted to the gun director Mark 38 train receiver regulator to automatically move it to the left and to the right so it'll stay on the target. The range rate, that is transmitted by a synchro over to the Mark 13 radar console, and it's able to automatically move its range tracking apparatus to keep on the target. So why would you want to have the directors move themselves? Is it just because people in the director are lazy? Well, remember when I said the observed bearing pointer represents the ship's director? Well, that's not exactly the case, depending on how you look at it. It's like if you're watching this video sitting down, chances are your head is facing forward. But if you decide to watch battleship systems lying down flat, chances are you'll have to turn your head to the left or to the right. The video hasn't moved, but your perspective has changed because your body is moving. The same thing happens with your directors mounted some 116 feet up in the air. As your ship pitches and rolls, the director sways in the wind. So this is what you would see. Luckily, there's a separate system that automatically levels the telescope, but you'll still have to constantly rotate your director back and forth to bear on the target. I don't know about you, but being a director trainer would become a living hell pretty quickly if I had to do that manually. To compensate for this, the rangekeeper has a deck tilt assembly. It sees where your director is pointed and how the ship is moving with respect to level and cross level to compute and observe target bearing as if the ship were constantly level. We'll talk more about where these values come from later on. Not only does this mean your observed pointer won't be constantly moving back and forth, it also takes this deck tilt into account when sending increments of generated director train
to automatically move the director. So as the ship pitches and rolls, the director will move to keep the target in the crosshairs. The only thing you have to do is correct it if it's wrong. That's pretty cool for 1940s technology. The science of predicting is the result of the Bureau of Ordnance firing so many 16-inch projectiles in different scenarios that they came up with ways to predict where and when they will hit the ground. The predicting part of the rangekeeper aims the guns based in part on the relative motion rates generated from the tracking section, true wind, which we've already talked about before, and time. These dials represent the initial velocity of your projectiles, and it's something you have to manually calculate and set before firing. Think powder temperature.
So with what we've entered so far is the movement of our ship, movement of the target, movement of the winds, the initial velocity, and the drift. With those values, we calculate something called advance range.
Advance range is the range you're shooting for. It's present range plus all the extra range you'll need to compensate for the changing target position and the other natural factors that will act against your projectile during its time of flight. But the rangekeeper can't account for everything. Things like air density, Coriolis effect, Earth's curvature, and gun temperature will also affect the projectile's trajectory.
So if you remember back to Fundamentals of Fire Control Part 1, there's things that can happen to the projectile in the air during a time of flight that can make it increase or decrease range or move to the left or right. And that comes from our initial ballistic corrections worksheet. This is something that you would have to prepare ahead of time and enter into the rangekeeper before you fire. The reason we have an initial ballistic correction is because initial velocity changes. Temperature of the powder will affect initial velocity. The air density will affect how fast the projectile will move. And eventually it's going to make our projectile either move so many yards to the left, so many yards to the right, or we're going to be shot over or short. So since we have our initial ballistic correction, we have to enter that over to these deflection and range correction dials. So right now we have our left and right correction. So we have our total is going to be 20 mils to the right. So we enter that into our deflection correction, 20 mils to the right. Now we have our range correction, which our total tells us that we need 500 over. So if we have 500 over, we need to drop by 500. So our range correction, we're going to decrease that by 500 yards. But if you remember, we also have a correction for first salvo only. Since a cold gun performs differently than a hot gun, and this is the first time we're firing the guns, we're going to add another 100 to our range deflection. So I'm going to add 100 here, and you'll notice when I push this down, it keeps a running total of our corrections here. This dial here is deflection. So if you remember, deflection is how much you point the guns to the left or the right of the line of sight. And it says right here that 500 mils equals 0. And they really mean that. So right now it says 569, and so it's telling us that the amount of deflection that it wants is 69 mils.
The reason they make you subtract from the counters is it's a lot harder to make one that turns a drum to show a negative and then starts counting the opposite direction when the counter reaches 0 than it is just to add an arbitrary number to it.
You ever back to Fundamentals of Fire Control Part 2, what we get from our ballistic correction is called sight angle and sight deflection. Sight angle is how far we elevate our guns above or below the line of sight, and sight deflection is how much of the left and right we aim our guns to hit the target. The rangekeeper calculates these values for us. So right here it shows sight deflection. It's measured in mils, and it says 569. Sight deflection goes from 325 to 600. Now, since 500 is 0, that means the sight deflection goes from negative 175 to positive 100, which means we have more deflection range in the left. Why is that? So when you fire a projectile from a rifle barrel, the projectile will spin in a clockwise direction. This means that it will have a precession to the right. So you would generally be wanting to aim your guns to the left more because projectiles fired will always move to the right.
This is known as drift. Since the gravity is always trying to push the projectile down, the gyroscopic action is offsetting this force by 90 degrees, which is to the right.
Now this one here is sight angle. Its minutes is 2,000. Sight angle moves from 2,000 to 4,800 minutes, so it's actually 0 from 2,800 minutes.
A battleship's rangekeeper can get ballistic data faster and more accurately than any human can by reading a range table. It's actually quite simple. The ballistic computer consists of a number of cams for every range table, the input being advanced range, and the outputs are gun elevation and how long it takes to hit. When I see equations like this, I become cross-eyed and start to lose interest in the inner workings of fire control equipment. But there are no equations inside a rangekeeper. They are instead filled with shafts, cams, gears, differentials, and integrators. I don't know about you, but diagrams like this kind of make sense to me. Shafts connect to gears of other components that change their output. Would you be able to understand the inner workings of a mechanical computer by a mechanical layout like this? Let us know in the comment section below, and don't forget to like and subscribe. Coming from a computer background, I gotta hand it to mechanical computers. If the target is moving away, the rangekeeper will have to increase advance range. This means that the time of flight will also take longer. However, the prediction section will also have to account for this longer time and extend its predicted target location, which will again increase advance range. It's like a chicken and the egg paradox. The ballistic computer needs advance range, but the advanced range computer needs the time of flight. Try programming that into a modern-day computer. At this point, we have practically everything we need and we're ready to fire our guns. But all of our measurements and our subsequent calculations have assumed the ship is on something called a horizontal plane, perfectly level. But ships don't stay perfectly level. The rangekeeper Mark VIII has a trunnion tilt computer which subtracts level and cross level from the gun orders in real time. But how does the rangekeeper know where the ship is tilted?
But Mother Nature might have some other things in store for us that might be rocking our ship back and forth. If our ship's rocking back and forth, then our guns are connected to the ship. That means our guns are going to be moving too, which is going to mess up our correction. That's why we have the Mark 41 director, also known as the stable vertical. So the purpose of the Mark 41 director is to maintain a true vertical. With the rolling of the ship, the gyro in here is able to maintain its position in space because it's spinning so fast that it is no longer affected by the pitch and roll of the ship. What the Mark 41 director stable vertical does is it tells us the level that the ship is moving at the target and the cross level where the ship is moving side to side with respect to the target. You put the target bearing over here, and this gives us the reference point that the stable vertical uses for the values of level and cross level. Level and cross level are sent to the rangekeeper twice. The first time is sent is through these rods underneath this block here. The second time it is sent electronically over here to the level and cross-level receivers. This is used by the trunnion tilt computer. The trunnion tilt computer is used to correct for tilting of the gun's trunnions since they're mounted on the ship. The guns are going to be moving up and down, training left to right to stay level.
This is known as continuous aim and allows us to fire the guns from the hand firing key on the stable vertical at any time.
But the guns can only elevate at 12 degrees per second. If you're on really rough seas, you need to change your tactics. So we have something called selected level firing and selected cross-level fire. And the way this would work is instead of automatically leveling your guns, you would wait until the ship reaches a certain level, your selected level, and the system will automatically fire it. The system that actually fires it is right here. The way you would fire it is you would pull your salvo signal key, ready, set, fire, and you would hold down the automatic key. Now, when the automatic key is held down, it sets the circuit to these level and cross-level mechanisms. As the ship pitches and rolls, these bars will move back and forth. And once it goes to the certain point that you want for your selected level, it connects the circuit and the gun is fired automatically. There's also a mode called selected train firing. So if for whatever reason you can't turn your turrets or you don't want to train your turrets, you can set your turrets to a specified angle, and then when these things line up, you would say that you're ready to fire.
Needs to have these portable salvo and firing keys. I don't think they would ever use them, but they allowed you to stand in front of the range keeper and fire at the selected train point. So at this point, we've covered all the computing elements of the range keeper. That's tracking, prediction, with the ballistic computation, and stabilization. We now have our gun orders.
So how does this range keeper actually tell the ship where to point its guns? Well, that is done through synchros. But if you remember back to the episode we did about synchros, you'll notice that synchros are very weak. When you're moving a computer with lots of dials and gears, a synchro might bulk up under pressure and not give you an accurate angle. So one of the things they do in the range keeper is they split it out. So you have a fine synchro and a coarse synchro.
All of the gun orders are sent electrically through synchros located in a pedestal section of the range keeper. There are sets of synchros for gun elevation and gun train.
Another synchro that the system would use is sight angle and sight deflection. This is transmitted to the sight setter stations in the turret, the areas that are sitting behind the pointers facing aft. The most common synchro generator in this computer is the 7G. This thing is huge, even bigger than the one I have at home, and is designed to connect up to 18 synchros. But when accuracy is a requirement, a lot of times that's not enough, and you need a servo. So even with the fine and coarse synchro generators, when you're dealing with something where a small amount of change, something 45,000 yards away, it's going to make a big difference. So battleships need all the accuracy they can get. So not only are there two transmitters per train, one train is an indicating transmitter, the other one is the automatic transmitter. So when you hear them say match pointers sent to automatic, the stations in the turret are going to be manually setting their stations to the indicated. When they shift to automatic, it's the automatic synchro that takes over. That's 4 synchros. There are actually even one more transmitter for train, and that's over here on the corner. called train order information. That is sent over to these multiple turret train indicators. There's one of these in the turrets to make sure the turret is matching what the indicated train order says.
It also calculates and sends parallax range to the guns and directors. Since they're scattered about the ship, it allows them to all point at the target.
Alright, so we just fired a projectile and we have no idea if it hits the target or not. So what we're going to do is use these B-scope indicators from the Mark 13 radar here. So let's say we have both Mark 13 radars trained at the target. This is our forward readout, this is our aft readout. Now I'm going to mention again that this is the oldest radar on the ship. It was installed in World War II and it was still used up until the 90s. So obviously they're not on now, so I just pretend that these are what the scopes are showing. So this is what our B-scope would look like now. So this is our target, this little blob here. And this is our range line that is matched up with the target. And these echoes appearing out here are actually our projectiles hitting the water. So obviously we need to make some adjustments so these will hit the target. The question is, how much of a range correction and how much of a deflection correction? Now, each one of these bearing dials is 50 mils apart. And each one of these dots is 200 yards apart. So if we look at it, I would say maybe 10 mils to the left and maybe 300 yards down. I'm going to do 5 mils to the left and 300 down. So the spot coordinator is going to say left 10, down 300. So we enter that into our range correction and deflection correction. So for the range correction, I'm going to go down by 300 yards. And for the deflection, I'm going to go to the left by about 10 mils. So we fired the guns again, and this is what we get. So now our splashes are in front of the target. This one looks like the deflection is almost perfect. Now we probably want to add about 100 yards to our correction. So then we would go into our range correction and add 100 yards.
If the target doesn't change their course and speed, they will get hit. We don't have to worry about getting hit because, well, we're a battleship. The modifications made to these range keepers allowed it to stay relevant for almost 60 years. I also didn't cover the graphic plotter because the museum removed it from this range keeper to free up space and allow you to see inside. But let me know if you still want to see a video about that. I'd like to thank the people that spent thousands of hours designing these magnificent devices in the first half of the 20th century. I don't know how they did it, but we're all sure glad they did. I'd also like to thank the Battleship Massachusetts for providing pictures of their range keepers. In lieu of donations to me, please consider donating to a battleship museum like the Battleship Missouri. There's a link in the description that'll bring you to the USS Missouri Memorial Association website where you can donate to the nonprofit organization. Thanks for watching.